Now if we start like power cycles, the first one, and as we said, an example of this power cycle is heat engines, that we start explaining these heat engines in previous chapters. And we will start talking about the basic analysis consideration, and we will start with analyzing the ideal cycle we have. So as we said in previous chapter, most of power cycles, most of heat engines operate on cycle. Operate on cycle means, let's assume we have start at this point. So we have some changes happen. I will change the conditions from this point to this point. Then I will have changes happen to the condition from point number 2 to point number 3. Then I will have changes happen from 3 to 4. Then I will have a change to happen from 4 to return back to the initial point. So point number 1, this is my initial point. And at the same time, this is my final point. And this will be the same if you have PV diagram, like relationship between pressure and volume, what is happening to pressure and volume. And even if you plot it on TS diagram, temperature entropy diagram, you will have the same thing. You will have one point, and this point will be your starting point, and this will be your end point. Okay. The whole idea of power cycles or heat engines, as you remember, we need to convert thermal energy, which is Qn. We have it this simple, Qn, or in the previous chapter we call it QH. So we need to convert this input energy, this amount of energy you are adding to the working fluid in the reservoir source, to work. So we need to obtain work. And the efficiency of this one is calculated by thermal efficiency. You remember in previous lecture we said we have thermal efficiency, we have isentropic efficiency. Thermal efficiency, this is the efficiency for the whole cycle. Isentropic efficiency just for like individual equipment. We have isentropic efficiency for pump, isentropic efficiency for turbine, but for everything, for the whole cycle, all components of the cycles, then we have thermal efficiency. Okay, and this is the whole idea. Power cycles, heat engines, we have heat, and we need to convert this heat into work. This process is not 100% efficient. We have some losses happening. We have some heat is rejected to the sink. Okay, we have Q out or Q in. Because of this one, because of existing of this waste rejection, waste heat rejection, we have thermal efficiency that we need to calculate or we need to find. If you remember in this part, when we talked about chapter 1, we said if we have any curve, any process, like this process, for example, that we are moving from point 1 to point 2, and regardless of what we have on the X and Y axis, so anything that you have in the X-axis or Y-axis, the area under this curve will represent the amount of work we are obtaining from this process. So this is why, for this figure, we have here PV diagram for cycle. So this is cycle, this represents power cycle or heat engine. So now the area between the all lines of the process, we have this area is representing the amount of work obtained from this cycle. Okay. If you want to like see this one, for example, so here we can area under, again, this one is the net amount of work we are obtaining from the cycle, the useful work we have. Because we have, when we just explained, we have this line, this process. If you go down to this process, this can give you like this area, like let's call it 2, 3, 2 star, 3 star. So this area can give you the amount of heat or the amount of work specifically in this process. But again, for the whole cycle, if you need to know what is the net amount of work obtained from the whole cycle, so this will be the area that we have, the confined area between the lines that representing the whole steps or the whole processes we have in the cycle. So again, for this one, if you go from this point to the X-axis, this point from the X-axis, this will give you work only for a single process. But for a whole cycle, just we have the area confined between the all lines that representing all processes, all the steps we have in the cycle. So if you can increase this area, if if you can increase the area between the points 1, 2, 3, 4, then this means we are increasing the network. So this means we are increasing the efficiency. If you are decreasing this area between point 1, 2, 3, 4, so network obtained decrease, then the efficiency decrease. So as long as we can increase the area that's between point 1, 2, 3, 4, if you can increase this area, then you can increase the network obtained, then this means the thermal efficiency will increase. Clear? Any questions so far? Okay. In order to analyze the power cycles or heat engines, we have an ideal cycle, an ideal heat engine that we have. And when we are talking about ideal, so this means we will assume that all the changes, all the processes we have in this like engine will be reversible or irreversible. Which one is ideal? Reversible. And this is what is called the Carnot cycle. So we have here power cycle. The first example for this one is Carnot cycle, and this is the ideal power cycle or ideal heat engine we can have. So this Carnot cycle, it says we have, or this is considered ideal power cycle or ideal heat engine. All the processes, all the steps, all the changes we have in this cycles are reversible changes happening. Everything is reversible. This cycle consists of 4 steps, as you can see here in the figure. The first step, we have some heat added to the working fluid while the temperature is constant. And temperature is constant, this is called isothermal. So the first step is isothermal heat addition. We are adding heat and the addition of heat happening at the constant temperature. So if you are adding heat to a working fluid and this heat will not change the temperature, so what will happen to this working fluid? If you add heat to any working fluid, we have 2 options, right? The first one, you remember, we have sensible heat, that the temperature of this working fluid will change. This is why it's called sensible heat. But if the temperature will be the same, and at the same time you are adding heat, so what will be the possible change we have for this working fluid? We have sensible heat and we have latent heat, and latent heat causes phase change. Okay. So we have isothermal heat addition. We are adding heat to the working fluid, but the temperature is isothermal, temperature is constant. So here in this step we have phase change happening to the working fluid at the same temperature. And if you have phase change happening to the working fluid, so Carnot cycle, this is considered the gas cycle or vapor cycle. Remember the classification? So we have gas cycle, we have vapor cycle. Gas cycle, we don't have phase change. Vapor cycle, we have phase change. So here in the first step, it clearly says we have isothermal heat addition, we have phase change what happening to this working fluid. So Carnot cycle is an example of vapor cycle. Clear? So this is the first step we have here. We have isothermal heat addition. The second step, we have expansion happening, and this expansion happens while the system is insulated. There is no heat transfer between the system and surrounding. So this one, or this step, is called adiabatic expansion. So this will be the second step. So you have isothermal heat addition. We have adiabatic expansion, expansion happening to the working fluid at like constant heat transfer or zero heat transfer between system and surrounding. Then this step, we have TL is constant. Since TL is constant, so we have isothermal. And here, as you can see, we have amount of heat is released. So we have this step is called isothermal heat rejection. This step is completely opposite at this one. Here we have isothermal heat addition. And here we have isothermal heat rejection. So step number 1, step number 3 are opposing each other. Here we have adiabatic expansion. So step number 4 will be the opposite to it. It will be, since we have insulation, so it will be adiabatic. Here we have expansion. The opposite for it will be compression. So these are the 4 steps we have in the Carnot cycle. So 4 steps, each 2 are opposite to each other. 1, 3 are opposing each other. 2, 4 are opposite to each other. 1, isothermal heat addition. 3, isothermal heat rejection. 2, adiabatic expansion. 4, adiabatic compression. So by this way, you can ensure that your final condition will be the same as your initial condition. You have working fluid, you are adding heat to this working fluid. You have expansion happening to this working fluid. Then you are removing heat from it, so you are cancelling the effect of step number 1. Then you have compression happening, cancel the effect we have in step number 2. So we return to the initial condition and complete the cycle. Clear? So we can see this one here. Let's see what is happening to the temperature and the pressure in this one. So let's assume we start with this state. We start at T1 and P1 for this working flow. So we start with adiabatic compression. So what is happening in this adiabatic compression? In this adiabatic compression, you will see the temperature will increase and the pressure of the temperature. Sorry, we have isothermal expansion, not this one. So for this step, we have state number 1, we have working fluid at temperature T1, at pressure P1. So this one will be supposed to, subjected to isothermal expansion. So what is happening to this step? The temperature and the pressure will change to T2 and P2. But since this process is isothermal, to T2 and T1 are the same. So we are changing the pressure, only the pressure. T1 will be constant, but we are changing the pressure. Then, this is a state number 2. We have T2, which is equal to T number 1. And we have P2. We have adiabatic expansion process. So what will happen? We have temperature and the pressure will change in this process. From state number 2 to state number 3. Then, we have isothermal compression. So we will change the temperature from T3, P3 to T4 and P4, but here since the process is isothermal, so you don't have any changes happen in the temperature. The 4th step we have here, we will return the conditions from T4, P4 to the original one, T1, P1. So this is the whole idea. We are doing everything and opposing this process to return to the same initial condition we have here, and then we will start the cycles that we have one more time. Clear? Any questions? In the diagram that we explained, we showed that we can represent the whole cycle in 2 diagrams, TS diagram and PV diagram. Usually for reversible process, it's much easier to use TS diagram, temperature entropy diagrams. Okay? Because if we need to plot the Carnot cycle, so as we said, Carnot cycle, we have 4 steps. And these 4 steps are reversible. And this is an example of the 4 steps. Isothermal heat addition, step number 1. Then we have isentropic turbine, reversible adiabatic expansion. Then we have isothermal heat rejection. Then isentropic compression, reversible adiabatic compression. So these are the 4 steps we have. If you need to plot or to use TS diagram to see what is happening on this one, so we have this curve, if you remember, this point from chapter 2. This is the critical point, critical temperature. Any point on this line is saturated liquid. Any point here on this line is saturated vapor. And any point here under this curve is mixture of liquid and vapor. So we have point number 1. This is point number 1 is going to isothermal heat addition. So point number 1, the working fluid at this point number 1 is saturated liquid. So we have here saturated liquid. So here at point number 1, we have saturated liquid. This saturated liquid will go to the boiler, for example. In this boiler, it will have isothermal heat addition. So the temperature will not change, but what will change is the phase. So the working fluid will change from point number 1 to point number 2. So here the outlet is point number 2, we have saturated vapor. This saturated vapor will go to a turbine where we can obtain more. And it will change from point number 2 to point number 3. So point number 3, this is the outlet of the turbine. So this is point number 3. This one will be mixture of liquid and vapor. Then this mixture of liquid and vapor, you will change to point number 4 through an isothermal heat rejection. So we have mixture of liquid and vapor will be subjected to isothermal heat rejection in a condenser, for example, and then the outlet also will be mixture of liquid and vapor. So if 3 and 4 are both of them mixture of liquid and vapor at the same temperature, so what is the difference? Just the fractions of the liquid and vapor. Point number 3 is more vapor. We have more vapor, more than the liquid. Point number 4, we have more liquid, or have liquid more than the vapor. So here at point number 3, at this one, we have vapor more than liquid. Here at point number 4, we have liquid more than vapor. But both of them mixtures, both of them at the same temperature. Just the fractions of the phases exist are different from both points. When we have mixture of liquid and vapor, we'll go to the compressor. It will be compressed in a reversible adiabatic. So to return to point number 1 again, which is saturated liquid, and then start a new cycle. Clear? So this is everything we have in this process here. And if you need to put this one, so here this is point number 1, this is the boiler inlet. Point number 2, this is the inlet to the turbine. Point number 3, this is the inlet to the condenser. Point number 4, this is the inlet to the compressor. So in the problem, you can see that I tell you the conditions at the compressor inlet is this temperature, this pressure. So we know that the compressor inlet is point number 4. The conditions at the boiler inlet. So we know that point number 1, this is the boiler inlet. Also in the problem, I can tell you the conditions based on the outlet. So the outlet from the compressor, the outlet from the turbine. So we have the same naming you can use here. So point number 1, this is the compressor outlet. Point number 2, we have here, this is the boiler outlet. 3, this one is turbine outlet. And here, number 4, this is condenser outlet. So condenser inlet, compressor inlet, the same as condenser outlet, and so on. So far as clear? The same thing, you can have the same diagram, you can represent everything, but instead of TS diagram, we can have PV diagram. And this will be the same thing we have for PV diagram. In the TS diagram, as you can see, we have all the lines either are horizontal or vertical. This is why we prefer to use the TS diagram. PV diagram, we have some inclination happening, but so far sometimes it becomes more difficult to represent, okay? But it's much easier to work with TS diagram. But the question why the TS diagrams have these lines, horizontal and vertical. As we said, we have 4 steps, right? 2 of them isothermal. And isothermal means we have constant temperature. So this is why we have this line represent isothermal change, this line represent isothermal change. And we have these 2 steps isentropic, reversible adiabatic, isentropic. And isentropic means what is constant? Entropy. So this is why we have this line is vertical, this line is vertical. So always we are representing this one. Always we prefer to work with TS diagrams. But if you calculate the area, like between the lines, this area and this area, both of them will be the same. Because both of them are representing the same cycle. Both of them are representing the amount of work obtained from it. Clear? Any questions so far? Okay. So again, here in the slides, as when I show you, you will see like detailed explanation of all the steps. Step number 1, reversible isothermal heat addition. You will see the description. What is the phase of the inlet? What is the phase of the outlet? The name of the unit we have here, and then what is happening. Step number 2, detailed description of this one. Step number 3, step number 4 for the Carnot cycle. So Carnot cycle is a heat engine, cyclic process. It's vapor cycle, consists of 4 steps. All these steps are reversible. 2 of them isothermal, 2 of them adiabatic. Reversible adiabatic means isentropic. So isentropic means entropy constant. So we have 2 steps, 2 processes occurs at constant temperature, 2 steps or 2 changes happen at constant entropy. Okay, clear? How we can calculate efficiency of Carnot cycle? So if you remember, we said that Carnot cycle is a reversible cycle. In general, for heat engine, this is the equation that we can use to calculate the efficiency of heat engine. But since Carnot cycle is a reversible, so we can replace the amount of heat added or removed from the working fluid at the sink and the source with temperatures. So we can use this temperature here that we also explained in previous chapter to calculate the entropy. Okay, so 1 minus the temperature of low temperature reservoir divided by TH, temperature of high temperature reservoir. This can be applied in Carnot cycle. Because this equation is only applied for reversible processes, and Carnot cycle is an example of the reversible processes we have. Okay? So let's see this example. This example says we have air. This air flows through a gas Carnot cycle. The air is heated to temperature 600 degrees Celsius. So this is the temperature that we are heating the working fluid to this temperature in the heat addition process. So this one representing TH, the temperature of the working fluid at the high temperature reservoir. And it's cooled to 200 degrees Celsius in the heat rejection process. So this one is TL, temperature of the working fluid at the low temperature reservoir. What is the thermal efficiency of this process? So the easiest thing for this one here, we have efficiency, thermal efficiency of heat engine in general is 1 minus QL over QH. But since we have Carnot cycle, then we can use this equation. Efficiency is 1 minus TL divided by TH. The only thing that you need to change in the given, yes, the temperature here you have is in Celsius, and in this equation we don't use like temperature in Celsius. So this one will be 1 minus TL, which is 200, plus 273 divided by TH, which is 600 plus 273. And then once you calculate the efficiency will be 0.4 58, which is equivalent to 45.8%. So this is the efficiency of this Carnot cycle. So this is the maximum efficiency that you can obtain from any cycle operating within this TH and this TL. Any real heat engine will have an efficiency lower than this value. So if you are solving a problem, for example, and you have real heat engine, and this is the temperature of the working fluid at high temperature reservoir, temperature of the working fluid at low temperature reservoir, and you calculate the efficiency of this real heat engine, and the efficiency is more than this number. So this means you have a mistake in your calculation, because this is the maximum efficiency we can have. We cannot get any efficiency more than this one. Clear? Any questions? Okay. So since we have this equation, so we can consider what are the factors So based on the equation, since we have the efficiency of Carnot cycle is 1 minus TL over TH, and only from this equation we can conclude that the efficiency of Carnot cycle, this one is function of TL and TH. Only the efficiency will change if you change TL or TH, not the fluid, not anything that you have here. Just this TL and TH can affect the efficiency of the Carnot cycle. So if we see this simulation of Carnot cycle efficiency, this is Carnot cycle for ideal gas, and again you can have the representation as PV, pressure volume, or in this website you can have the presentation as TS diagram, so you can have it as TS diagram. So the area that we have like between these two lines, this is representing the net amount of work we are obtaining from the cycle. If you can increase this area, then you can increase the efficiency of the cycle. So here we have the efficiency is 29%. We have the temperature of the cold reservoir at 250 Kelvin, temperature of the high reservoir 351. So you can see here, if you like increase TC, for example, like make it 300. So now if we make it 300, we can see, so this area, this curve will change, this area will become smaller, and then the efficiency, instead of it was 29, now it becomes 15%. Okay, so if you can keep increasing the temperature of the TC or the lower temperature, then what is happening to the efficiency? Decrease. Okay. On the other side, if we have TH, the hot reservoir temperature, if you increase the temperature of the hot reservoir temperature, so what is happening? The temperature starts to increase again. So again, if you increase it, so this is always when you are increased TH, so the area is increasing, efficiency calculations here also increase. So according to this Carnot cycle, you can increase efficiency of the Carnot cycle by two ways. If you have TH, so what you need to do with TH? Try to increase it. Okay? If you have the lower temperature of the working fluid, you try to reduce it. Only these two options you have. So always you can increase TH or decrease TL. So let's see the maximum we can have on this website. So the maximum, if we have TH is 650 and the TL or TC is 250, so this is the highest efficiency we can obtain at this condition, 62%. Clear? Okay, so now the efficiency of Carnot cycle is only a function of these two temperatures. We can increase the efficiency by increasing TH or by decreasing TL. Clear? So the last thing that we will talk about today is the limitation of Carnot cycle. So we said Carnot cycle is an ideal cycle. It doesn't exist in nature. In real life, Carnot cycle cannot exist because we have some limitations for Carnot cycle. And this limitation comes from this path. So most of the limitations come from here. Come from point 3 and 4. Because point number 1, we said it's saturated liquid, just one phase. Point number 2, saturated vapor, still one phase. Point number 3, point number 2, both of them are mixture of liquid and vapor. And in general, it's very difficult to have an equipment that deals with two phases. So you can have many equipments that you can handle liquid phases, can have many equipment can handle vapor or gases, but if you have mixture of liquid and vapor at the same time, so this means you need special equipment for this one. And this is the main limitation we have for Carnot cycle. So Carnot cycle, as we said, we have the isentropic expansion process, process 2 to 3. This one, it yields mixture of liquid and vapor, which is point 3. At the same time, so what is happening? Here we have step 2, 3. This step happening inside the turbine. This turbine has some plates, contains impellers. Okay, so this impeller, if you have mixture of liquid and vapor, the liquid droplets will cause impingement or collisions with the plates of this turbine plates, and it can destroy it. It will have erosion happening to this one, it have wear happening to this one, it can destroy totally the plates of the turbine. So this is the first problem we have. So process 2, 3, this process 2, 3 happening in the turbine, and this process yields mixture of liquid and vapor, and the problem here, if we have liquid droplets goes into the turbine, so this liquid droplets will impinge or hit the plates of the turbine and can destroy it. Okay, so this is one problem that we can have in Carnot cycle. That makes us, in real life, it's very hard to have turbine handling these two phases. The other problem is the isentropic compression, process 4.1, this process that is happening inside the compressor. The inlet to the compressor is point number 4. And point number 4 is also mixture of liquid and vapor. And again, it's very hard to have a compression for liquid vapor mixture at the same time. With the same thing, we have some plates in the compressor, and the compressor is designed just to work with vapor. We have pump, can be used to compress liquids. We have compressor used to compress vapor or gases. But we don't have an equipment to compress two phases at the same time. This is very hard to achieve in real life. Okay. So just in a summary, you can say we have two difficulties associated with the saturation process. As we said, it's not easy to control the condensation, and it's not practical to design a compressor that handles two phases. So all the problems we have with the mixture of liquid and vapor, we have at point number 3, outlet of the turbine, point number 4, inlet to the compressor. These things makes Carnot cycle is very hard to be obtained in real life. Just we are using it for the analysis. It's an ideal process. It will give you the maximum efficiency. So just we are having it to calculate the maximum efficiency of our process. Okay? But we can't have a real Carnot cycle in real life because of these limitations we have.